some of at least my work on DNS for understanding of multiphase flow. So I'm currently work in the group of multiphase and reactive flows leading by Niels Steen. But I have to mention that the work involved in this presentation were done in the group of Hans as our chairman. And so, as you can see from my outline, I have a very simple, clear presentation, and simply because compare most of you in the audience, I don't really have that experience, not much experience on the scientific research. And so I will first explain why I think DNS is so important. And then I will give 3 examples of how we use DNS to study these 3 problems. And then I will come to the conclusion. And why is DNS such important in understanding the small scale physics in multiphase flow? And first, in DNS, you can see that from this picture that all the continuous scales are solved without using any subgrid models or some major assumptions. And all the initial and boundary conditions as well as the forcing are clearly defined in the system. And the simulation can product all the detailed data for every single variables. And of course, in this case, it also requires very large computational power. And therefore, DNS is currently limited to small domains, and the device scale simulations are out of reach. Even though DNS play a significant role in fundamental studies of the small scale physics of multiphase flows, and it also constitutes a powerful tool for the development and validation of reduced model descriptions used in meso and macro scale CFD simulations. And in this presentation, I will give you 3 examples of how DNS play such role in our research. The first application is gas fluidized bed. I don't think for this audience I need to spend a single word on the introduction of the fluidized bed, so I will skip this one. And for modeling of fluidized bed, we use a multi-scale approach as indicated in this figure. It's connect 3 levels of simulation method. And from DNS 223 model, you have the computed geometry is increased, but less details are resolved in the systems. And the role of DNS playing in this approach is to derive the closures for gas-solid interactions, which are usually the key input for DNS, for DEM simulation and TFM simulations. And to perform the DNS of gas-solid system, we use an immersed boundary method in this project. And this immersed boundary method follows the approach proposed by Ullmann method. And the gas phase is governed by Navier-Stokes equations on the Irving grid, and all the particles are tracked, of course, and following the Newtonian momentum equations. And the gas-solid interaction force is calculated based via enforcing a no-slip boundary condition on the surface of the particles. And each particle, you can see from this figure, each particle is represented by a set of marker points. And we specially use an optimal diameter for the location of the marker points. In this case, you can see from the right-hand side, and the marker points are located slightly inward the interior of the particle surface. And why we do that? And because when you calculate the IB force based on each single marker point, then you have to project the force back to the grid nodes surrounding, and this projection leading to a great dependency result. So if we use this optimal diameter, then you can see from this contour of the slip velocity nearby the single particle, is that the no-slip boundary condition in this case is exactly fulfilled at the surface of the particle. And consequently, if we plot the dimensionless drag force along the grid resolution, you can see if we use the optimal diameter, then the results can be independent of the grid resolution. Sorry. And if you use without, then you simply get to the problem. And so this IBM model is first validated by the experiment of a small pseudo 2D fluidized bed. And so experimental measurement, we use the techniques like particle image velocimetry and digital image analysis. I will not spend too much word on this. And a very simple but clear defined system is used for the validation purpose. And so we first look at the right-hand side. The right-hand side, the top is the snapshots from simulation, IBM simulation. Right at the bottom, the pictures recorded from the high-speed camera. So you can see a relative comparison between these two. And similar flow region are both predicted. And you can see the big bubbles formed and travel through the bed. And now we move to the left-hand side, where we give a quantitative comparison for the time averaged volumetric solid flux at different bed height. So you can see that a very good agreement can be achieved between simulation and experiment. Of course, you can see that a little slightly difference, but a reasonable difference is present nearby the wall boundary. And so with this validated model, we performed a systematic numerical study for the gas-solid systems. And we also study at a very wide range of solid volume fraction, and also a wide range from real number from almost 0 to 1,000. And computational domain composes of 108 particles in a periodic 3D box. And those particles are either fixed location or they can freely move. So there are two cases of simulations. I will tell you why we do that. And especially for the moving particle case, we also take into account a different density ratio. And this figure, we plot the dimensionless drag force as a function of Reynolds number for the particular case of the packing fraction 0.4 at density ratio 500. And those dots are our simulation for the moving particle system. And you can see a few lines. And those few lines are the correlation from the literature. And most of you are familiar with them. And this line, the solid line, is our simulation for the stationary system. And when we compare those dynamic system and stationary system, you can always see that the drag force is increased. So this is not surprising, because this enhancement of drag force can be attributed to the particle velocity fluctuation. And so we proposed a Reynolds number, which is defined based on the slip velocity between the gas velocity and the particle velocity fluctuation. And in this figure, we also found that there is a very clear correlation between this new defined Reynolds number on the mean Reynolds number, which uses the slip velocity between the gas phase and the mean and particle velocity. And of course, in the end, we want to derive a drag correlation. This is what we get. And it looks complex, but it has a reason in it. So the first two terms correspond to the drag force in stationary particles, which normally you can find from other correlations in the literature. And it's a function of the mean solid volume fraction and the mean Reynolds number. And we also add an extra term which accounts for the mobility effect. And this is a function of this we call it granular real number and the solid volume fraction. So I don't have here, but recent publication from other researchers have demonstrated that with use of our correlation in the CFD-DM simulation can better predict the realistic dense gas solid flow. So this is the first application, and then we move to the second application, and where there is a liquid injection in the gas flow that's bed. And you also see some introduction from our plenary talk, but I will extend the introduction a little bit. And those kinds of process are usually found in industrial process like granulation, agglomeration, coating, etc. So the injection of liquid induce a layer of liquid around the particles. So those particles are wet, and when the particles collide with each other, then they agglomerate, of course. And the collision behavior of the wet particles are fundamentally different from the dry particles. And, and in that case, this different collision behavior leads to a dramatic change in macro-scale flow behavior. It can be demonstrated in the experiment here. So we have experiment of fluids bed in dry condition. As long as we inject together a little amount of water, then you can see the bed dynamics dramatically change. But if you stop injection and wait until the particle get dried, then the same fluidization region come back again. So this tells us if you want to model this kind of process, that means it also requires a very accurate quantification of each individual collision of particle with the presence of liquid. That is where the DNS can contribute. And this kind of problem is commonly simplified into a case with a spherical particle impacting on a wet surface with a very thin liquid film. And you can see from this sketch, actually the complexity lies on the formation of a liquid bridge. And this figure plots the height along the time for a particle impacting on the plate with or without liquid layer. So you can see that the peak height after bouncing back of the with liquid layer is much lower than the dry case. That indicates that the particle lost more energy during impact due to the presence of the liquid layer. So the total energy dissipation is quantified by a restitution coefficient. And for the wet case, we define this restitution coefficient as a ratio of the velocity of the particle exactly when the liquid bridge is ruptured to the impact velocity where the particle just gets into touch to the wet surface. And we perform DNS to study this restitution coefficient at different conditions. And again, in this project, we again combine experimental measurement and DNS approach, try to look at the detailed restitution coefficient. The final goal is, of course, we want to make use of those data to derive a model closure for the restitution coefficient, which can be simply plugged in a larger simulation. And we use a combined method of VOF and IBM. IBM already introduced before, and the VOF method is also followed in standard method. You can find the details from these two papers. And simply, there is surface tension force is introduced in the momentary equation of the fluid phase, and you use color function indicates the solid, indicates the fluid fraction at each cells, and the density, local density and local viscosity are dependent on this color function. And the surface tension force is calculated based on a tensor force model, which is a function of surface tension coefficient and a cross product of the tangent and normal at the interface. And this unit normal is calculated as a first derivative of the color function at the gas-liquid interface. But here we are dealing with three-phase flows. So at the gas-liquid solid interface, three-phase interface, then we modify this unit normal based according to the wall adhesion boundary condition. So in this case, it is calculated based on the an enforced contact angle and the normal and tangent of the solid surface. And here I show you the experimental validation for this for our simulation. You can see. Okay, let me. Sorry. I have to also show this video. So these are simulation video and experimental recording. So you can also get quantified comparison between these two videos that they both reveal a similar process of the impact. And we look deeper, and those are quantitative comparison. And first, this is the plug of the particle velocity along the time, and the dots are experiment data, and the line are from our simulations. So first impression, you can see already it's very perfectly agreed with each other. But that's not all you can get. You can also see from the right snapshots comparison that both our simulation can reproduce the whole period of the impact. So you can, from A to F indicates the different phase. For instance, the A, you have the first contact between particle and the liquid surface, and this is A to B is the penetration of the particle through the liquid film, and then at this C, then particle gets contact with the plate, and then start to bounce back. Then a liquid bridge is formed, then get thinning, and then finally break up. And the velocity, particle velocity at this liquid breakup and the impact velocity, between experiment and simulations are exactly matched, which means that we calculate the same restitution coefficient as can be measured from experimental. So this this constitutes perfect validation, and with this validated model, we carried out many simulations. For instance, this is the restitution coefficient. Okay, I'm always bad at the pointer, sorry. So this is the restitution coefficient as a function of the impact velocity. So you can see that at critical velocity, the restitution coefficient is 0. Simply means that the particle dissipates the full energy and it gets stuck into the wet surface. And with increasing impact velocity, then the restitution coefficient also steadily increase and towards a constant value. And we also look at different parameters, for instance, different particle size and the viscosity of the liquid, and also the thickness of the liquid layer. So we found out the restitution coefficient is linearly increased when you increase the size of the particle, but it is dramatically decreased when you increase the viscosity of the liquid, and when you also increase the thickness of the layer. So, with all our simulation data, we want to come to a single model or closure for the restitution coefficient in wet systems, and this is what we did. you can first look at the figure, and the big circle symbols are from our simulation data. And we first try the model proposed in literature, which is commonly used in other literature where the CFD, DM simulation or two-fluid simulation are using. But we found out it simply failed of the prediction of the restriction coefficient. So then we start to look around what is the correct description. And we found out in the end this is a very good combination. And this express use definition of the stock number according to Ma et al. This paper. And we also use, instead of using the dry restriction coefficient, you should also use an infinite restriction coefficient, which of course depends on many parameters. And this is also from other research paper, but you have to combine them together. And okay, if you combine these two together, then you can see from the pink symbols, it does a very good job already. But we found it's even better if you use this critical stock number differently, then you can have a perfect match with simulation data. But it's a pity at this stage, this critical stocks number is still dependent on our experimental measurement, and it require further study if we want to have a simple correlation for it. And so this is the correlation if you are simulating the wet system and in larger scales. This is a correlation you probably can make a note now. Okay, so this is the second application. And the final application is the macro structured bubble columns. So you will see some of the results already seen from yesterday's presentation of Hans, but I look at it into a different perspective. And the simple brief introduction or background behind this project is that by inserting the wire mesh at desired locations, then the bigger bubbles, you can see, I play once again this experiment demonstration, and the big bubbles will be cut into small bubbles, and then the smaller bubbles will induce more vigorous dynamics and therefore enhance the mass and heat transfer of the system. And the design of this new bubble column, of course, can benefit from the CFD simulations using a discrete bubble model. But if you want to have a correct prediction from DBM simulations, you also require some fundamental inputs which can be learned from DNS simulations. And this is how I look at it for this project. Again, VOF and combined IBM method is used for this research. And the first fundamental study we did is to look at the drag force inserted by the wire mesh you installed. And the wire mesh is approximated by the unit cell of two cross cylinders, and characterized by the spacing of the wires and the diameter of the cylinders. And the IBM simulation is performed for the liquid passing through the single unit of the cross cylinders. And here is the simulation result and the drag coefficient as a function of real root numbers for different case of the ratio, the spacing diameter ratio. So you can see that if you increase this ratio, and then the drag coefficient also decrease. Ideally, and of course that's what we want, you would want all those data present here to collapse on a single line. Then you can derive the single correlations. You can achieve that by introduce or scale the drag coefficient with the void fraction of the wire mesh. So you can see that by doing this, by this scaling, then all the symbols collapse on the single line, and this is the correlation proposed based on this fitting of the data. And this correlation will be used in the DBM simulation of the new bubble column reactor. And the second fundamental study for this project is to look at how the bubbles are cut by this wire mesh. And you already see this from presentation of Hans yesterday, that the experimental snapshots and the DNS snapshots, experimental measurements agree very well with the DNS simulations, which constitute a perfect validation for our model. And what we want to get from this kind of DNS simulation is we want to get the data or to provide some insight for the bubble cutting mechanism. For instance, this figure proposes the mechanism of the cutting. You have first a parent bubble, a big bubble, goes through the wire mesh, and then it will be cut into a few daughter bubbles and also remained bubbles with the size depending on the spacing and also the size of the wire mesh cylinder. So in the end, if we use that correlation we derived earlier and also the cutting mechanism and derived from DNS into the DBM simulation of bubble column, you can see that this is successfully performed for the cutting bubble column. And the comparison of the between without wire mesh and with wire mesh is also clearly indicates the smaller bubbles are formed after the wire mesh. And we plot the mean bubble diameter plus the column height. This is where the mesh is inserted. You can also see a dramatic decrease of the bubbles, which demonstrates what we want to propose in this project, that the bubbles are cut into smaller and more dynamically, and therefore enhance the process. And so that's my presentation. And by giving these three examples, I want to deliver the message that the combination of DNS and experimental investigation is an efficient approach to study the small-scale fundamentals at the multiphase flows. And in my future work, I want to extend my work with DNS to multiphase flows where the nanoparticles also exist. Thank you.
Thank you very much, Jali, for your presentation. It's open for